In this module, we'll explore about graphs and graph theory. Probably you might have got a pinch of this module in discrete mathematics also. First, we'll concentrate on the formal definitions of graphs, and then we try to discuss about practical applications and their implementations. Formally, a graph is defined as set of pairs of vertices and edges. V is a set of vertices or nodes. E is a set of edges which joins the nodes. The graph G is a pair of these set of vertices and edges. For example, we can consider a graph for example, if we happen to have a set of stations and a road network which joins them is a graph. Similarly, a set of stations and the train rail network which joins them is also another graph. Probably set of stations, places, and 8 traffic routes is a graph. Even we may encounter in our house also a graph. For example, set of wires and switch boxes in electric wiring. It is also can be considered as a graph. Maybe water supply system can be considered as a graph. So thus there are many concepts or many areas where we can represent a problem in a graph and we can deal with those problems. As time progresses, we shall be highlighting about these applications. So in a nutshell, a graph can be defined as a set of nodes and edges which joins them. Graphs are commonly classified as directed graphs and undirected graphs. Directed graphs are the ones in which edge will be having some direction, whereas undirected graphs are the ones the edges will not be having any direction. For example, in a road network, some roads are one ways, which means that the traffic can be allowed in one direction only. There are some roads on which the traffic can travel in both directions, like that. The edge, if it is undirected, means like that the traffic can go in both the directions. In the same fashion, directed means traffic can go in one direction only. So such a type of graphs we may find. The nodes which are adjacent to a node, they are called as the adjacent vertices of that node. That is, the nodes which has an edge connected to a node are called as adjacent vertices of that node. Path is a sequence of edges from one node to another node. A graph is said to be connected if there exists a path from any node to any node in the graph. A graph is said to be labeled graph if its vertices and edges are labeled. For example, the nodes, if we consider as cities, and the roads which joins them as the edges, if we name the vertices, that is nodes, with the city names, and the edges, that is the roads, by the set of them, if we write the distance, then that graph can be said as labeled graph. A subgraph of graph having nodes V and E edges as a pair of vertices V dash and E dash, where V is a subset of V dash is a subset of V and E dash is a subset of E. That is, we can consider is a portion of a graph is called as a subgraph. A connected component containing the node U is a subgraph containing all the nodes of V that may be reached from U by traversing 0 or more paths, or what we call edges. Neighbors of a vertex V are all elements of the set V, the set of nodes, which are having an edge from V. Of course, already we understood they are called as adjacent vertices. Similarly, the degree of a node V is equal to its number of neighbors or adjacents. Already we understood about what is meant by a path. Similarly, a cycle is a one which is between one node to another node. So if we can reach from one node to another node via a series of edges, then that is called as a cycle. If you start from a vertex and if you can again reach the vertex via many edges, then we can say that that is a cycle. For example, we can see this slide where we find some graphs with two components. First graph is having two components. Similarly, we have a labeled graph where the edges are given some weights. At the same time, we have right hand side of the slide a graph having a cycle. In degree of a node is the number of edges ending at the node. Out degree of a node is number of edges leaving or emanating from the node. Degree, that is the total of in degree plus out degree. A vertex is said to be sinc if its out degree is 0. Similarly, a vertex is said to be, or a node is said to be source if its in degree is 0. A free tree is a connected graph without a cycle. Usually, the number of edges in a free tree will be the number of nodes minus 1. A graph which is having no cycles, rather I say a directed graph without any cycles is called as a directed acyclic graph or DAG. Graphs can be represented in the computer memory in many ways. For example, we can store only in a set of edges fashion, or we can maintain in a adjacency matrix fashion, adjacency list fashion, or adjacency sets fashion. In adjacency matrix representation, we'll be having a matrix of size n by n, where n is the number of vertices or nodes in the graph. The ith row, jth column element of this matrix value indicates how many edges are there between the ith node and jth node in that graph. The main or rather I say advantage of this one is ease of visualization. However, this matrix that's called adjacency matrix will be very dense if the number of edges are more, that the graph is very dense graph, then the elements of this matrix will be very dense. Otherwise, the matrix is a sparse matrix. The main drawback of this representation is its huge memory requirements. That is, we require n square elements. In the case of adjacency list, for every vertex, we maintain a list of adjacent nodes. In a linked list fashion, adjacent nodes details are maintained. The advantage of this is memory requirements will be less, especially for sparse graphs. Usually, rarely we encounter dense graphs. Thus, if we store the graph information in adjacency list fashion, memory requirements will be less. Adjacency set is a simple variant of adjacency list, where adjacent vertices of a node are not maintained in a linked list fashion. They are maintained as a set, such that sometimes searching can be done in the better manner. In this slide, we may find the adjacency matrix of the previous graph. Also, its adjacency list is also shown. You can verify that the adjacency matrix contains ones and zeros. Ones indicates from the respective node to the respective node there is a edge. Zero indicates there is no edge. Whereas in the case of adjacency list, we may find that for every vertex or node, its adjacent informations are maintained. Adjacent vertices details are maintained in a linked list fashion. See the figure. This slide demonstrates the difference between adjacency list and adjacency set. So in the case of adjacency list, adjacent vertex details of a node are maintained in a linked list fashion, whereas in adjacency set, we may find that the adjacent nodes are maintained in a set fashion. The memory requirements of graph representations. If we store only edges, then the space required is E, where E is the total number of edges in the graph. In the case of adjacency matrix, we require V square locations. In the case of adjacency list, E plus V locations. In the case of adjacent set also, we require E plus V. However, evidently, either adjacency matrix or adjacency lists are commonly used. The following table compares the trade-offs between these two representations. We may find one is having advantage over other in some respects. For example, to test whether there exists a edge between one node to another node, if that is our requirement, then adjacency matrix is very easy. Just simply we can verify ith row jth column element whether it is there or not, whether it is 1 or not. Whereas in the case of adjacency list, we may have to traverse entire linked list of that vertex and to find out for another vertex. Then only we can decide whether there is a edge or not. Also, in the case of the application where if you want to find out what is the degree of a vertex, so probably here adjacency list is easy. Adjacency list requires less memory compared to adjacency matrix if the graphs are sparse graph. However, if the graphs are dense, then matrices is easy. They consume less space compared to adjacency lists. As in adjacency list, we may require to maintain the addresses, etc. also. Insertion, deletions of edges is comparatively easy in adjacency matrix approach compared to adjacency list. However, traversing the graph is easy in the case of adjacency list compared to adjacency matrix. However, there are many other applications where adjacency lists are preferred over adjacency matrices, which we may discuss in the following slides. So this is a nutshell comparison of adjacency lists and adjacency matrices of graph representations. We have a variety of graphs known as grid, complete graph, complete bipatrite graph, wheel, Möbius wheel, etc. Each one we may find in different applications. This slide will demonstrate or shows graphs for grids, complete graph, bipatrite graph, wheel, Möbius wheel, Voronoi diagram, etc. The adjacency matrix of a graph indicates the number of edges available from one node to the another node. The adjacency matrix is not necessarily binary valued matrix. If there exists more than one path from one station to another station, then the respective element value in this matrix will be same as that number. Path matrix of a graph, which is also called as reachability matrix, it indicates that whether one station can be reached from another station or not. That is there any route from one station to another station or not? It doesn't convey any information about how many edges we have to traverse, etc. It indicates only whether from one station to another station is there any route or path or not. For example, for this graph what we have taken, we may find that the first row except for first element remaining all are ones, indicating that from the station A we can reach all other stations. Of course, the station B can be reached with one edge, whereas others requires more number of edges to be traversed. The path matrix will not convey that one. Similarly, if we see that is D to E is 0, which indicates that there is no route from station D to station E at all. Similarly, the path matrix last row is completely zeros, which indicates from station F you cannot go to any other station, including itself also, indicating, of course, it is called as a sink. Of course, the station D is also sink because that respective row is zeros, indicating that from D you cannot go anywhere. All the edges ends at D. So like this we have path matrix will convey this type of information. Let us have some discussion on adjacency matrices and others. For example, if A is adjacency matrix, of course we assume that A is a binarized version of the adjacency matrix. Binarized means that if an element value of matrix, adjacency matrix is greater than or equal to 1, it will be considered as 1, otherwise it will be taken as 0. So that's, we are assuming the matrix A is adjacency matrix, but binarized version of it. A is that one. Then A into A matrix we have calculated in this slide. You can verify the matrix product. What it will convey? It conveys that from one station to another station, is there any path with two jumps, or by traversing two edges can we reach from one station to another station or not? That is the information it conveys. For example, in the resultant matrix we have second row fourth element value is 2, indicating that there exist two routes from B to D with two jumps. You can verify the same in the graph. That is, we can traverse via B to C and D or B to E and D. So that way we can physically verify. This number 2 indicates that B to D there exist two routes with two jumps, or that is by traversing two edges we can reach from B to D by traversing two edges. What are those paths? B to C, C to D, and similarly B to E and E to D. Like this matrix, resultant matrix will convey this information. Similarly, if we again calculate A into A into A cube, what it will convey? It conveys that from any station to any other station, is there any route with three jumps, that is by traversing three edges or not. Like this, if we happen to have n stations, then A to the power of n matrix indicates is there any route from one station to another station by traversing the n edges or not. That is the information it will convey. After calculating A to the power of n and binarizing the same, we get the path matrix. However, this is a crude algorithm. Warshall proposed a algorithm to calculate path matrix given the adjacency matrix. It requires only OR and AND operations. It uses the fact that to say that there exists a route from station I to J, there can be a route from I to K and K to J, then we can say there exists a route from I to J. Basing on this concept, the algorithm is designed. This involves only Boolean OR operations and also AND operations. Initially, the path matrix P is considered as the binarized version of the adjacency matrix. From that we'll start, and by running the above for loops shown in this slide, we get the final path matrix P. The complexity is very less compared to the previous method of calculating A power n and then applying the binarization for that. That may require a lot of efforts, whereas this one doesn't require much efforts. Common operations on the graphs are inserting a vertex, deleting a vertex, inserting an arc or edge, deleting an arc or edge, traversing the graph, etc. In addition to some other problems such as finding out the minimum spanning tree, finding out the best route, or finding out all the best routes, etc. This slide demonstrates depth first search algorithm for a graph as a whole, or depth first searching from one graph, one node of the graph. We'll be demonstrating in separate modules about depth first search algorithm in detail. Just for the sake of explanation or understanding, this algorithm is given here. depth first traversal of a graph starting from a vertex V can be said as, first we'll mark the vertex V as visited, and then for all unvisited vertices of V, we call the depth first traversal recursively. This is the essence of the depth first traversal algorithm. If we apply depth first traversal on the following graph, the output will be A, X, H, P, E, Y, M, J, G. Usually for the depth first traversal, people employs queues also. In the next slide, we will demonstrate how a depth first traversal of a graph can be carried out with a graph. Also, the following slides will demonstrate the recursive traversal of the graph using depth first traversal. First, the node A is now till the stack is empty. We follow the following procedure. We pop a node from the stack and mark that node as visited, and all its unvisited nodes will be pushed into the stack. Thus, now the node A will be popped out from the stack and it will be made as visited, and its neighbor or adjacent node, that is X, is now pushed into the stack. Now the node X is popped out from the stack and it is marked as visited. Its two neighbors G and H are pushed into the stack. Now H is popped from the stack and its two neighbors E and P are pushed into the stack. Now P is popped out of the stack, it is made as visited, and its neighbors are supposed to be pushed into the stack. However, P doesn't have any neighbor to be pushed into the stack. Now E is popped out of the stack, it is marked as visited, and then its neighbors, both M and Y, pushed into the stack. Now Y is popped out of the stack, it is marked as visited, and its unprocessed neighbors are pushed into the stack. However, already M is in the stack, so though M is a neighbor for Y, it is not required to be pushed because it is already there in the stack. Now when we pop out from the stack, M will come, it will be marked as visited, and its neighbor J will be pushed into the stack. Now J is popped from the stack, it will be marked as visited, and its neighbors are supposed to be pushed into the stack, but no neighbor is available for J, so nothing is pushed into the stack. Now G is popped out from the stack and it will be made as visited. By this time the stack became empty, thus will come out from the program. So this way stack is employed to traverse the graph in depth first manner. The output of this graph traversal is A, that is the node first made as visited, then X, that is the node which is made as a visited next, like that H, P, E, Y, M, J, G. This is the depth first traversal of this given graph. In the following slides, we will demonstrate how the depth first traversal on a graph can be carried out using recursive function calls. First, we consider directed graph, that is, the edges are having directions. The graph is as shown in the slide, and the right hand side we have displayed the vertices and their adjacent vertices details in adjacency list fashion. The following slides will demonstrate how the recursive depth first traversal algorithm works on this graph. We are trying to show each time when a function is called how recursive function calls will be made. We will be showing activation records to indicate how the recursive calls will be really growing, and again they will be getting rewinding. So let us assume that first the DFS function is called by sending the vertex A as an argument. The function call stack is as shown in the slide. Remember, A has two edges, that is AF and AG. The algorithm says that on both the adjacent vertices we have to call the DFS algorithm recursively. Let us assume that DFS f is called. Thus, the function call stack is as shown above. Now we have an edge from f to e, which means that we are supposed to call the DFS function recursive call on e now. When the function DFS is called on e, the function call stack will be as shown in the slide. E has edges EC, ED, EG. So on all those vertices CD, CDG, the DFS function is supposed to be called. When the DFS function is called on C as an argument, its neighbors, that is CA, CD is the edges. So A, D are the adjacent nodes for C. However, A is already in visited state, so no action takes place on A. However, D is another neighbor for C. D is not in the final state. Thus, DFS is called on D again. Now the function DFS is called on D. D's neighbors are C and F. However, C is already processed. Also, F is already in the final state. Thus, the DFS function is not called on F also. Previously on C also it is not called, and now on F also it is not going to be called. The DFS function returns to the previous function call. That is, a rewinding takes place. Again, function calls comes out of this function call. Now the function call stack is as shown above. Now for the vertex E, there is one more unprocessed vertex G is available. So on that, the DFS function will be called now. Now the DFS function is called on G. The control comes out from the previous function call. Now the function call stack is as shown above. Again, rewinding takes place. Function call returns to the previous function call. Again, call comes out from the function call. From this function also, return take calls. Nodes reachable from A are A, C, D, E, F, G. So like this, depth first traversal algorithm works. However, in this example, we have demonstrated how to find out the nodes which are reachable from A using this depth first traversal logic. In the following slides, we will demonstrate the same thing on undirected graphs. The graph is as shown in the slide. Incidentally, you can verify that it is having two connected components, and the adjacency list will display what are the adjacents of each node. In this algorithm, we try to take some assumptions, make some assumptions. Nodes are said to be undiscovered, are marked, are active, are finished. We assume that we are starting the graph traversal from A. A's adjacents are F, C, E, etc. Initially, we consider F, all of them are undiscovered. Now, first F is discovered. A state is said to be active state. Now, we try to take F and its adjacents. They are considered, and one of them is made as discovered. Now E is made as newly discovered node. On E we apply the algorithm. Its neighbors, that is G, is made as newly discovered node. G's neighbors, that is E and A, they are already marked. Thus, no action takes place on them. Now, G is made as finished. That is the widgeted node. Function call returns back. D becomes newly discovered node. Now, the function call will be done with D. However, its neighbors are already in marked state. Now, D is made as finished. That is, widgeting is completed. Again, function call returns back. F is marked as finished. Now, C becomes newly discovered node. Function call is made with C. Its neighbors, for example A, it is already in marked state, so thus nothing takes place. Now C will be made as finished. Now B is made as newly discovered. A function call will be made with B. When we verify B's neighbors, B doesn't have any undiscovered nodes at all, so no action takes place. B is made as finished. A's other neighbors such as G, it is already in the finished state. No action takes place on it. Now A will be made as finished. Now again DFS is called with H. I is the undiscovered node of H. So a function call is made with I now. I doesn't have any more or any undiscovered nodes. Thus it will be marked as finished and function call will be returned. Now H also will be made as finished. Like this, stack can be used to traverse graphs which are not having directed edges. In the following slides, we will demonstrate breadth first traversal of the graphs. The main essence of this algorithm is as follows. We take a queue. First, we start from one node. We push or we mark it as visited, and then we insert all its unprocessed or unvisited nodes into the queue. Then we go on take one item or one vertex from the queue and mark it as processed or visited, and then we try to push all their unvisited nodes into queue again. This is repeated till the queue is empty. So in the algorithm we have shown visited as black and unvisited as white if they are in the queue as gray. Only for our convenience purpose we have used. The following slides will demonstrate how this algorithm works. Main theme behind breadth first traversal is as follows. That is, all adjacent vertices are processed before the descendants of a vertex. For example, in the following graph, first we will start from A and then X, its two adjacents G and H, and then P, E, M and Y, and then J. That's how the nodes are visited. That is the breadth first orders traversal sequence of this graph. Next slides will demonstrate how really the traversal takes place on a graph. Let's consider the graph shown in the slide. We assume that a queue is used for breadth first traversal. First, the starting node is inserted into the queue, that is enqueued into the queue. From wherever we want to start, that node will be pushed into the queue. Now we dequeue a node from the queue. Visit the neighbors of the node A. The neighbor B is pushed into the queue. Neighbor I is also pushed into queue. We assume that the node A has reached the finalized state. Like this, we have to proceed and till all the nodes of the graph reaches finished states. Now we dequeue an item from the queue. That is, when we dequeue, we get B from the queue. Visit all the neighbors of B and push them into queue if they are not in the finalized state. The node F is pushed into the queue. A is also neighbor to B. However, it's already in the finalized state. That is, already it is discovered. Thus, it will not be pushed into the queue. We will be pushing the nodes into the queue only if they are not in the finalized state or a discovered state. No more adjacent nodes are available for B. Thus, B will be made as finalized. That is, its state is made as discovered. Now again we dequeue an item from the queue. That is, I will get from the queue. For this node I, we have to check up its adjacents, and if any of the adjacents are not in finalized state, they will be pushed into the queue. E is pushed into the queue. All the adjacent nodes of I which are in the unfinished state or undiscovered state, they are moved into the queue. Now I will be made as finalized. That is, it is declared as discovered state. This time again we dequeue an item from the queue. That is nothing but F. Now all the undiscovered nodes of F will be moved into the queue. G is pushed into the queue. F is made as finalized. Again we dequeue an item from the queue. Incidentally, that becomes E. E is made as finalized. Now again we will dequeue an item from the queue. That becomes G. C is pushed into the queue. H is pushed into the queue. G is made as finalized. Now again we dequeue an item from the queue. That becomes C. D is inserted into the queue. C is made as finalized. Again we dequeue an item from the queue. That is, H is the item or node coming out from the queue. Its neighbors will check up. If any of the neighbors which are in the not in final state, they will be pushed in the queue. However, incidentally, all the nodes are in the ready state. Thus, they will not be pushed into the queue. H is made as finalized. Again, we'll dequeue a node from the queue. We get D. When we check up, all the nodes of node D are in the finalized state, so no node will be coming into the queue. Finalize the state of the node D. Now there are no more nodes in the queue. Rather, all the nodes of the graph are traversed. This style is known as breadth first traversal. Here we have used queue for the traversal purpose. The sequence of the nodes which are kept in the finalized state are A, X, G, H, P, E, M, Y, J. So that is the breadth first traversal of this given graph. In this slide, we did show the number of nodes in the queue when this algorithm is applied on this graph. We do have some problems where we are supposed to find out some routes or paths having minimum weights, etc. Some applications we require this type of facilities where we may be having graphs known as weighted graphs. Here for each edge there will be a number associated with them known as weight. That number can be distance between two stations if we assume that each node is one station or one place, or maybe if we assume that each vertex is a router point in a computer network, the number may be delay at that time or something else also. So this such type of graphs are called as weighted graphs. For this type of graphs, the adjacency matrix may look like the following. For this type of graphs, adjacency list may look like the above. In some applications of this type of weighted graphs, we require to find out spanning trees, minimum spanning trees, etc. Spanning tree is the one which contains all the vertices in the connected graph. However, the minimum spanning tree is the one which is a spanning tree, but the sum of its weights are minimal. It has some implications in the practical applications. For example, if we wanted to send or broadcast some message to a set of nodes from one node, from that node we have to find out the minimum spanning tree. Along that route the packet has to be sent such a way that the packet will be reaching all the people, that is we wanted to broadcast in the fastest possible manner. That's how the minimum spanning tree use in practice we may find. There are a lot of applications, of course. In some applications, we are interested to find out shortest route from one node to all other nodes. Of course, remember, this is little different from the minimum spanning tree. The route what we are required to find out for all other nodes should be minimum, whereas minimum spanning tree gives minimum in a global sense, tree as a whole sense, whereas here the roots whatever. For example, this is the graph, and below the graph we have shown all the possible spanning trees. In this graph we have demonstrated a weighted graph and its minimum spanning tree. Let us consider another application. We have some set of applicants. P, Q, R, S are the applicants. We do have set of jobs. We are referring them as A, B, C, B, D, A, E, E. These are the jobs. Those applicants are suitable. However, no applicant is accepted for 2 jobs, and also a job cannot be assigned to 2 applicants. The problem is to find out a worker for each job. This can be represented with a graph where the applicants P, Q, R, S, T are one nodes, the jobs A, B, C, D are another nodes, and based upon their suitability, we are showing the edges. For example, P, he can do jobs A, B, C. So thus we have shown edges P to A, P to B, P to C, and similarly others also. Now we can identify that by applying some graph theory problems that for P we can assign a job B, for Q job D, for R job A, for S job E, for T graphs job C. Thus we are able to assign one job for one applicant. This type of problems requires the concepts of graph theory. Another popular problem is called as graph coloring problem or map coloring problems. We have a map with different regions. We are supposed to use minimum number of colors to fill the regions such that no 2 adjacent regions will be allowed to have the same color. We are required to find out what are the minimum number of colors we have to use to carry out this. This problem also can be brought to the graph coloring problem. Next slide will demonstrate a simple example. One possible solution. Another possible solution. Also, graph applications are available in many other applications, in project planning, and also many applications known as scheduling, etc. In the slide, we have shown a set of activities with vertices and how much time is required to complete that and go to the next stage. They are given in the edges along with hours associated with it. So we are interested to find out the critical path. The red path is called as critical path. That is the one which takes the longest time compared to all other routes. Graph applications are available in the memory management also. There is a method known as mark and sweep garbage collector which employs concepts of graph theory. And all the objects are allocated, they are maintained in the graph, and when something is required to be freed, so it will be traversing in the entire graph, and those things which are marked as free, they will be removed. This technique is called as mark and sweep garbage collector. It uses the concepts of graph theory. Sometimes graphs can be used to represent the set related concepts. Also, expressions can be represented in a tree, parse tree fashion, where tree is nothing but acyclic graph. There are many applications known as flow problems. They are available, they are used in many areas known as communication systems, circuits, mechanicals, hydraulic, financial, transportation, water supply systems. Many places we have graph theory concepts can be used. For example, in a communication system, telephone exchanges, computers, satellites can be considered as nodes, whereas the cables, fiber optic lines, microwave relays, etc. can be considered as arcs, and voice, video packets, they are the flow. We may encounter some problems related to finding out the best route or heavily loaded path. Maybe sometimes it may be static or dynamic, etc. We are supposed to find out. So all these problems are classified as max flow problems. They are solved using the graph theory concepts.